So I found out that I can use the colors in the black background and you can see them a lot better than you could on the white background. So we're going to switch over to black backgrounds for most of the slides. So we're going to go back and do one of the problems from last class because I want to introduce a new concept, not with the problems that you did last class, but just because I want to do it with something you've seen before, then going into the new thing and introducing something on top of that as well tonight. So we're going to use something that we've already done that you should know how to do from last class, give you a little bit of review of that, and introduce the new little piece to it. So we got sine to the third x and cosine to the fifth x. So we got to figure out which one we're going to make u and which one we're going to do our derivative of that. Since cosine's the bigger one, they're both odd, actually, so I could choose either one of them. It doesn't make much difference. Since cosine's the bigger one, I'm going to set u to be cosine. So u equals cosine of x. So du is negative sine of x dx. No, I forgot the dx there. All right. This is the piece that is different. When you do, when you do u substitution in a definite integral, I can change the definite integral, the range, to be u instead of what's there. This means I do not have to go back and plug back in. I can actually solve it in terms of u. Now, in most situations, not going to make that big of a difference. In tonight's lesson, when we actually do it, you're going to see why it makes a big difference. Because it's going to save you a ton of work. All right? So we're going to look at it in terms of this. So all we do is we're going to plug the two numbers that they gave me into what u is. So since u is cosine of x, u of 0 is cosine of 0, which is 1. And then u of pi over 3 is cosine of pi over 3, which is 1/2. Okay, so we're going to change everything in this problem to u's. And then we also have the, remember the trig identity, it's sine squared x equals 1 minus cosine squared x. So let's change everything over. So my 2u pieces here, that's the 1, because 0 became 1, and the pi over 3 became 1/2. Now, sine 3x is sine squared x times sine. So I'm going to make the sine squared x the 1 minus, and that's u squared. Cosine to the fifth x is just u to the fifth. And then that sine and that dx is going to be negative du, because I bring that negative sign over. Now you know why I wanted the colors. All right. Everybody see what I did there? So the goal is to change everything into terms of u. Now, when I solve my problem, when I actually solve the derivative or the integral of u, I don't have to go back to x. So I don't have to change it back into, change all the u's back to cosine x. Okay, and then evaluate it. This only works when it's a definite integral. If it's not a definite integral, you still have to go back because we'd want in terms of the original variable. All right, so now we can clean up this problem a little bit. So I've got negative 1 to 1/2 u to the 5th minus u to the 7th du. Anybody notice something strange about this integral? Unlike any other definite integral you've seen. Yeah. Normally, the numbers are kind of in order, right? It's 0 to 1, 1 to 5, but this is 1 to 1/2. So those numbers are backwards. We didn't do anything wrong. It just happens to be the way the cosine works, right? Cosine goes down. So we can swap them. So this way we don't have to worry about sign errors and stuff like that at the end. You can swap it. All you do is change the sign of the problem. So I can change this to, since it's a negative, I can change it to a positive and do 1/2 to 1. So all you do is you change the sign that's in front. So if it was positive, I would have made it negative. In this case, since it's negative, I made it positive. Yes. So the sine to the third became sine squared to the sine. This sine squared x became the 1 minus u squared. That sine x went with the dx with the d. All right. Any questions with where we are right now? We only got basically one step left to do the integral and then plug in the values. So
-5 plus u7 because you said you switched the sign.
I didn't switch the signs. I switched the sign of the integral. So because there was a negative sign already out in front,
yes,
I made it positive.
So it just like changes the direction.
Yeah.
Yeah. Okay.
Yeah. So if there was no sign there, I would have made this negative, and it would have been the same thing. So you're not actually changing the whole thing. You're just pulling out that sign. All right. All right, so now we just got to do our integral. So I've got u to the 6th over 6 minus u to the 8th over 8. And we're evaluating this in 1/2 and 1. So I have 1/6 minus 1/8 minus 2 to the 6th power is 64. And 64 times 6 is, I can't do it in my head. Hold on. Thank you. And then 2 to the 8th is 256. 256 times 8 is 1,000. No. Well, 8 times 200 is 1,600, so it's more than that. No, 2,044.
Yeah.
Is it 20 or is it 2048? 2048. Okay. Okay. Now, again, you don't necessarily have to sit there and do out the fractions. This is what happens when I make up problems. It always come out to be nice. But that's okay. Because we have decimals. So we had 1/6 minus 1/8 minus 1 over 84 minus 1 over 2048. Like that. So we have 81 over 2048. And that's the answer. The only thing that changing it to back to u it helped is I didn't have to go back and change the u back to cosine of x and then plug back in do exactly what I would have done there. I'd have plugged in 0, I would have plugged in 1/2 or pi over 3, and they would have come out to be the exact same thing. It just saved me that step. And a lot of times that step doing it at the beginning is easier than trying to do it when you have a bunch of pieces at the end that you'd have to plug it into. So it's one of those things that I just haven't shown you yet. And it's going to come in handy in the next lesson that we're going to do. So I figured show you on something that you've already seen. All right. Any questions with that? Okay. Now on to trig substitution. So if we're looking, let's see if I can make this a little darker. So we have, actually, so if I wanted to find the integral of a squared minus x squared, right now, there's not much I can do with this. So, because actually, I'm going to change the a just to a number just to make this a little easier so people can see. Let's say that. So if I wanted to find the integral to that, how would you, if you looked at that, what would be one of the first things that you'd want to try to do? Okay, how would you break it up?
It wouldn't be square root 4 minus.
No. But thank you for saying that, because that's a very, very important thing to actually recognize that it's not. This does not equal that, because that is 2 minus x, 2 plus x. So we could turn it into a power, but what's that going to help me do? What do you mean the substitution rule?
No, I think it's just
What did you say?
I was going to say something. I stopped myself.
Oh, okay.
I thought about it halfway through.
So if we change it to a power, we still just have 4 minus x squared to the 1/2. It doesn't really change the problem. Does it give you an idea of what else you can try? Yeah. That's why you can't split it up like that. Yeah, you can't split a square root like that. So one of the things that a lot of people try to do is, well, try u substitution. If you have something inside of something, typically that's one of the methods that you try to do. So if we try u substitution, let's say u 4 minus x squared. So then du would be what? Negative 2x. So this would be fine if I had an x. So since I have nothing else around this square root, there's actually nothing we can do for it. So with what we have right now, you're kind of stuck. Okay, we don't have a method to do a substitution here to figure it out. However, this format, 4 minus x squared equals y, like the square root, that's the equation of a circle or an ellipse, depending on how complicated the thing is. So remember, the formula for a circle is x squared plus y squared equals r squared. So the equation for a circle comes up quite often. So we need to have some method to be able to find area within a circle or an ellipse. So since u substitution doesn't really work, we need another method. So what we're going to try is what's known as trig substitution. So instead of making you instead of making you a piece in it, I'm going to change X. I'm going to say X is a sine, or actually in this case, I used a number, 2 sine theta. So I'm just going to change what X is. X is now 2 sine theta. What's dx? What's the derivative of cosine? Oh, sorry, sine. Thank you. It's cosine. I had cosine already in my head. So it's 2 cosine theta. D theta. This is where this piece really comes into play. Okay. So all right, so we've got that. Now let's change things. So we're going to take this integral, and now I have the square root of 4 minus 2 sine theta squared times 2 cosine theta d theta. Yes.
So 2 sine theta come from, or why 2 and not some other number A?
You'll see in a second.
Okay.
All right, let's clean up this square root. So this now becomes 4 minus 4 sine squared theta. So I'm just going to deal with the square root now for a second, and we'll deal with the rest of the stuff in a minute. 4 times 1 minus sine squared theta. Now that becomes 4 times cosine squared theta, which is 2 cosine theta. Okay. Oh, I know. I'm not going on yet. Does everybody see what I just did there? All right. So you asked why I used 2 instead of some other number. It's because I wanted a number that was going to work with the number I already had. So if you remember it at the very beginning before I actually changed it, it was a square. So that number that you're going to put next to the trig function will always be the square root of whatever number you already have there, because you're going to square it, and then I can pull it out. The goal is to get rid of root so that I can now do an integral for it. So we can now take this problem that I have, so right now I have the integral of 2 cosine theta times 2 cosine theta d theta. Because I have that 2 cosine theta and that 2 cosine theta. All right, so I have the integral of, I'll pull the 4 out so I don't have to deal with the 4. The integral of cosine squared theta d theta. Now, what was the identity we used last class for cosine squared theta?
Half plus 1 cosine 2x. Theta.
Yeah, in this case, so this is one of those situations where the symbols matter. Because we've switched from x's to thetas, and I'm going to have to go back to x's. No, sine is minus. I'm almost sure.
Yeah, sine is minus.
Yeah, the sine was the minus one. All right, so now we can do the integral of this, right? So I can pull out the half, so it's now 2, 1 plus cosine 2 theta d theta. So I have 2 theta plus, or actually, yeah, this plus 1/2 sine 2 theta plus c. So I can do 2 theta plus sine 2 theta plus c. I'll give you a second to process. So I pulled out the 1/2, which is why that 4 became a 2. I took out that 1/2. And now the integral of 1 is theta. And now remember, when you have something inside, you have to do the implied u substitution by pulling that number out, and it's the fraction of it. So that's where that 1/2 sine 2 theta comes from.
Right.
And now I just multiply it by 2 to get rid of the parentheses. So that's like a 2 theta plus sine 2 theta. I'll switch back in a second. Don't worry. All right. So we have this now. And originally, we had all right. So I have what x is, right? But I need to know what theta is. So let's solve that for theta. So I have x over 2 equals sine theta. And then I have theta equals, or let me just the other direction. So keep say theta on the same side. So I have sine, the arc sine of x over 2 is theta. So for this problem, we're going to stop here. You're going to see in a minute we're going to go further than this. But for right now, I'm going to stop here for this one. It's just going to look really messy. So what you're going to do is you're going to replace theta with what theta is, which in this case is the arc sine of x over 2. We're going to make the problems look a little better in a minute. So that's what trig substitution is. The key piece, though, is what do you make x? You have to make x something that's going to work out for you. So the main part of this whole thing is figuring out what x is going to be. And that's going to be based on what you have in the problem to start with. And that's what this slide shows you. So, can you see that? All right, let me see if I can find a that's really like blown out.
Okay, that's not gonna help.
All right. I guess I right. So if you have a squared minus x squared, that's the one we just did. X is going to be a sine theta.
Where a is the square root.
Where a
Value.
so a is what a is in the problem. So with the term that's there, so in the last problem, 4 was there.
Yeah.
So a was 2. Because 2 squared would be the 4. So the number that's there in place of where a squared is not a, it's the square root of a. Yeah, so you have to take the square root of whatever's there to find it. If we have a squared plus x squared, x is going to be a tangent theta. And if we have x squared minus a squared, x will be a secant theta.
And then, can we just simply use this thing?
Oh yeah. Yeah. Well, so yes, but all this is going to do is give you that. That's literally all it's going to do. All the rest of the stuff you still have to kind of do out. You're going to get better. So the piece that you're going to get really good at that you won't have to do out is this one. You're going to be able to, hopefully, you're going to be able to look at this and say, okay, this is what it's going to come out to be, and you won't have to do all these steps up here. So I'll have to do the integration part and switch it back. So, but that's the ones that we're going to have. Because if you look at it, the goal is to make something that I'm going to use to work. So the first one, that's going to end up being sine squared. So we're going to use sine squared theta equals 1 minus cosine squared theta in there. Oh, actually, the opposite. The opposite direction. We have cosine squared theta is 1 minus sine squared theta. For the tangent, sorry, you're going to have 1 plus tangent squared theta equals secant squared theta. And for the secant one, you're going to have secant squared theta minus 1 equals tan squared theta. So, because the goal is to get something that's there into a something that I can now just do the square root of it. It's the same as a squared plus x squared. Remember, addition is committed. I can switch it back and forth. Subtraction, you can't. That changes it. So if I had x squared plus a squared, I could literally just reverse those and you still be able to do the tangent one. X squared plus a squared is the same exact thing as a squared plus a squared. So the minus ones, you can't do that because it changes the sign. Well, yeah. We're not using those. Because remember, the goal isn't actually to do the trig stuff. The goal is actually to take something that I cannot take the integral of and take the integral of it. So the problem that you're going to have isn't going to have trig functions in it. It's going to have just a square root in it. So these are the ones that'll take care of all the variations of the square root for ellipses, hyperbolas, those type of things. Circles. All right. Let's look at one.
Is that a 9?
Yes, it's a 9. That's a 9. All right. So what am I going to make my x? Yep. And then my dx is 3 cosine theta d theta. Now, unlike when we did substitution before, we were solving things to bring it over and get the dx by itself. In this case, my dx is already by itself. All right, so now we have to substitute everything. Let's clean up the square root, and then we'll substitute over and actually do out the calculation for it. So if I had the square root, I got 9 minus 3 sine squared theta squared. So it's 9 minus 9 sine theta squared. So 9, 1 minus sine squared theta. 9 cosine squared theta is 3 cosine theta. So you can start to see, if you look at this, okay, this does not always come out to be exactly what that is. Don't take that way. But it's going to end up being A and then the rule that you're using, just that simple. So it'll be the cosine, it'll be secant, it'll be tangent, depending on which one of those 3 options that you're using. So because the pattern for this is literally always going to be exactly the same steps. All right, so now that we've got basically everything converted over into thetas, I got to plug everything back into the problem and see what I got. So so the top I know is 3 cosine theta. X squared is 3 sine theta squared. And dx is 3 cosine theta d theta. Any questions with how we did the substitution and stuff back in? The big piece to this is you shouldn't have any more x's. Everything has to be in terms of theta at this point. Okay, so no matter what happens at this point, you can't have more than one variable. Okay, that would be a very bad thing at this stage. All right. Now we got to clean up the integral and do the integration. This is one of those ones where you want to try to do as much cleaning in reducing and simplifying as you can before you do the actual problem. So I have 9 cosine squared theta over 9 sine squared theta d theta. So I just put the top together and got rid of the parentheses on the bottom. Now what do I have? Yeah, the 9s can cancel out, right? And then I have cosine squared theta over sine squared theta, which is what? The reverse of it, cotangent. So I have cotangent squared theta d theta. All right. Do we know the derivative of cotangent squared theta? No, it's not secant. It's actually not one that we have a ready rule for. But we can change it to cosecant. Cotangent squared theta is cosecant squared theta minus 1. So now I have the integral of cosecant squared theta minus 1 d theta. And we might think, well, that doesn't help me very much, but we do. But cosecant squared theta actually does have a very nice integral. The integral of cosecant squared theta is cotangent theta minus theta plus c. So one of the things that you're going to want to have handy when you're doing your problems is at the beginning of chapter 7. I couldn't tell you the page line that you can't see it on the screen. The beginning of chapter 7 is a list of integrals, basic integrals. You want to kind of have that handy. All right. Somebody asked last class, but I'll reiterate this class. The review test and the test will be very, very similar in problems. So if you need the integral on the review test, you will probably need the integral on the actual test. You will not have an integral you will not have a crazy integral on the actual test that I will not have on the review test. So if you need the integral of cosecant squared theta, because that's not one that you typically are going to remember, it will be both on the review test and the actual test. So write it down. Okay. If it's the integral of sine, that's the one that you should just know. So that could show up on the actual test and not be on the review test, because that's one I would expect you to know. Okay. So, but the oddball ones like this one or the arc sine one, things like that we talked about before, those ones I wouldn't expect you to know off the top of your head. So I will have them on both tests. All right. Are we done? Huh?
Still trying to convert it back.
I got to convert it back to X. All right. So let's look at this one. So in this problem, we have, in my original problem had X equals, was it 3 sine theta? Yeah. So X over 3 is sine theta. Now we have to remember our trig rules. Which two sides is sine? Opposite and hypotenuse. So if we were to make a nice little right triangle here and make that theta, that's X, and that's 3, because that's opposite over hypotenuse. Okay? I'm going to give you a nice little trick. The other side is always the square root they gave you. So in this case, this is going to be 9 minus X squared. Was it minus, right? Yeah, 9 minus X squared. So the other side you technically can do the Pythagorean theorem to figure it out, because you would have a squared plus X squared equals 9, and then you move it over and take the square root. But it will always be whatever square root you started with is the side that's missing. Okay? So, what's cotangent? What's two sides? Adjacent over hypotenuse. So, adjacent is square root of 9 minus X squared over hypotenuse. Or not over hypotenuse, over opposite, which is X. And then theta is just the arc sine of X over 3 plus C. So to convert it back, you kind of got to remember your right angle trigonometry. What's the wonderful little saying that they probably taught you at some point? So katoa. Very handy, very helpful. Okay. To remember which pieces to go into where. Now, if you put what I just showed you here together with what I showed you at the very beginning of class, if we change things over to theta, before I don't have to do the whole right angle trig to go back. So it saves me that extra step at the end, which is very nice in these problems. Only if it's a definite interval, though. I did tell you, Scott, you were going to need the unit circle. All right. So SOHCAHTOA is going to definitely come into handy here. All right, let's try this one. First step, figure out what x is and clean up my square root part. So figure out x, dx, and then clean up my square root part. And then we'll plug it all in. So you want what x is, what dx is, and the square root of x squared plus 4 equals what? So this one was x squared plus 4. So you should be using the a tangent theta for this one. Even though it's reversed, remember the whole conversation, plus doesn't matter being reversed. So your x should be 2 tangent theta. Remember, you're taking the derivative of tangent here, not the integral of tangent. Your square root should simplify down into being 2 secant theta. Or what I said, they're not always exactly the same, so. All right, so if we plug everything in, 2 secant squared theta, p theta, that's my dx. It doesn't matter if you write it next to it or on top. Doesn't make a difference. In this case, there's a 1 on top anyway, so if there was something else on top, just put the other thing there too. The x squared becomes 2 tangent squared theta. Oh, sorry, 4 tangent squared theta. That's squared. And then the square root of x squared plus 4 is 2 secant theta. Clean it up a little bit. You can get rid of the 2's, and I can get rid of one of the c. So I have secant theta over 4 tangent squared theta. All right. The next thing, we're still not done cleaning this up and making it easier, because what we have right there is not going to be simple for us to be able to do the calculations on. One of the nice things that we can do is we can change everything to sines and cosines and see if that helps me clean things up a little bit. And sines and cosines work really well with integration and derivatives. So I'm going to pull out the 1/4. Secant is 1 over cosine. And tangent squared theta, if I put it up top, would be cotangent. It is cosine over sine. So I have cosine squared theta over sine squared theta. D theta. So I have cosine theta over sine squared theta. And so far, I've done no actual calculus. I've literally just done simplifying trig functions. Oh, we did one. We did the derivative. Sorry. We did one piece of calculus so far. All right. Now we still got to find the integral of this and switch it back. All right, so we have the integral of cosine theta over sine squared theta. Don't lose my 1/4. All right, so how do we want to do this one? Yeah, So remember, one of the nice things about going to sines and cosines is if we do u substitution, they switch back and forth. So if I make u sine theta, du is cosine theta, which I have. So I now have 1 over u squared du. So I have 1/4 times negative 1 over u plus c. So I have negative 1 over 4 sine theta plus c. So this right here is u to the negative second power. So we have to add 1 to that and bring it down. So it becomes negative 1 u to the negative first power. That's where the negative sign came from. And then I just do u's down the bottom. All right, so we start off this whole problem with x being what? Oh, 2 tangent theta. So 2 tangent theta. So that means x over 2 is tangent theta. So if we make our wonderful little triangle here, tangent is what? Opposite over adjacent. So that's there. And this would be x squared plus 4. So I have sine, or if I really wanted to be crazy, I can move the sign back up top. So this way I have it in terms of, I don't have to flip things over. But I'll leave it there for right now. So I have negative 1 over 4. And then sine is opposite over hypotenuse. So I've got negative square root of x squared plus 4 over 4x plus c. And we're now back to x. So we went from x to theta to u to theta to x. And 90% of the work we did was algebra. And that's why I say over and over again, your pre-calc and your algebra skills are going to be the most important thing to doing well in these tests. Because I'd be willing to bet if I just gave everybody simple integrations and simple derivatives, everybody would be able to get it right. It's being able to manipulate the problem to do what you want is going to be the tough part. And you also now see why, if this was a definite integral, I could have actually just done it with u's and never had to go backwards. So that definitely saves me some steps at the end. All right. 2 more. All right. Take 8 minutes. So I'll give you the 6:10. Get as far as you can in this problem. I need everybody to write the problem down because I'm going to mute the screen in a minute. So. Everybody got it done? So you can use some of this stuff. Help you out. Remember, we just did X squared plus 4. We started with it. So go back and use stuff that you already have. That's the direction you're going.
Said at the beginning of class too.
Huh?
You said at the beginning of class.
Two more minutes. That becomes secant. Wait. So that, oh, was it the, oh, it's a plot, right?
Oh, yeah.
Okay, so that's, yeah, that's 2 secant theta. That's right. I was just making sure that part was right. So that's that, yeah. And that was 2, and yep. So then we cancel that out. 1, so you have that. So it's a 2 secant theta. Okay. Of secant theta is what? Oh, so wait, that goes to secant. Oh, so the integral's gone. So it's the- okay, so then okay, so that's fine. You don't need your secant anymore. Too long for some.
Then everything gets
Where in your work do you make that mistake? Yeah, the two should be on this. So yeah, so we want half in the front and don't put your seat in there. Please replace. So that's what's there. One more minute till everybody's pissed off at me.
Oh, yeah, okay.
Huh?
I see.
That's the answer. Last two classes, I've mentioned one very specific thing over and over again, and I even did say it at the very beginning of this class. What is the first thing you should always look for before you do a problem? Use substitution. And in the very first problem of class, I had just the square root there, and I said, if we had an x, we'd be able to use substitution to make this problem really simple. You have the x in this one. Now, if you had gone through and did out the actual trig, you'd have gotten the exact same answer. Okay? There was nothing wrong with you doing the trig that way to do it out. The only problem is it took a lot longer. Okay? So I can guarantee you there will be a question on the test that looks one way that you could use substitution and make your life easier. Guarantee it. Okay? So I'm telling you, so just keep an eye out for that. Okay? So if you think about it, the last two classes I've done, or three classes actually, I've made sure to do at least one of those problems because you will always want to look for the simplest solution first. Right? Like I said, if you did it out the other way, you still get the right answer. It's just like if the sine and cosine are both odd, you can pick either one to do it. It'll still give you the same answer at the end. It just might not look the same. Well, that also could happen in this case. So, all right. Okay. One more problem. Hey, look, it's a definite integral. Because I haven't done one of those yet. But this one, I make the other math a little harder. Yeah. No, it's the it's the square root of the cube of it, technically, if you want to write it out that way. This, yeah. No, the cubed of that. The 4x squared plus.
Cube root.
It's a square root, not cube root. Squares, the two's on the bottom. Yeah, it's if you don't do your things right when you go through, you lose a number there. All right, so let's look at the same type of stuff that we've been doing in the other ones. I need to know what x is going to be. I need to know what dx is going to be. And I somehow need to clean up my square root, which in this case is 4x squared plus 9 to the third power. So what is my x going to be? Okay, which trig function is my x going to be? It's going to be tangent, right? So it's tangent of theta. Now, the question is what is a going to be? Somehow I need to change that 4 into a 9, right? So because I really want 9 tangent squared theta plus 9, correct? So somehow I got to change that 4 into a 9. So, and remember, I'm going to square it. So if I do 3 over 2, that would be 9 over 4, correct? Which would then change my 4 to a 9. Which I'll show you because I'll actually do out the square root so you can see it. All right, what's the derivative of this one? What's the derivative of tangent? Yeah. All right, so let's clean up the square root part so you can actually see how this one works out, and then we will do our use up or our theta things to get rid of my things so I don't have to go backwards. So I have the 4 times 3 over 2 tangent theta squared plus 9. So I have 4 times 9/4 tangent squared theta plus 9. So I have 9 tangent squared theta plus 9. Pull out the 9. I have tangent squared theta plus 1. So this becomes 3 secant squared, or 3 theta, 3 secant theta to the 3rd power. Don't lose the 3rd power. All right. So we've got what x is, we've got what dx is, we've got what the square root part is. Now I just need to figure out what the these two values here are going to be. So I don't have to go backwards. So those are x's now, correct? That's actually very, very important. So 0 equals 3 over 2 tangent x, or tangent theta. So which value of theta gives you 0 for tangent? Tangent of what gives you 0? 0. So that one's going to stay 0. And then I have 3 square root of 3 over 2 equals 3 over 2 tangent theta. So I got square root of 3 equals tangent theta. So which value of theta gives you square root of 3? So if you think about your unit circle, think about your unit circle, tangent goes from 0 to undefined, and it's at 1 at pi over 4. So then it would have to be higher than pi over 4. So it's pi over 3. And they're never going to give you one here that's going to be so crazy that you're not going to be able to just look at the unit circle and get it. So I've got that one and that one now. Yeah, I got to go back there anyway. All right, so we're going to take that crazy square root problem over there, and we're going to change everything into thetas so we can do some work with the trig parts. This, because I need both. All right, so we had the integral of. Okay, give me 1 second. Let me just rewrite the integral. Okay. Okay. So we have x equals 3/2 tangent theta. We had dx is 3/2 secant squared theta d theta. And then we had the 4x squared plus 9, that square root went to, what is it? 27 secant to the third theta. And then x equals 0 was theta equals 0. And x equals 3 squared of 3/2 is theta equals pi/3. All right, so we now have 0 to pi/3. We have 3/2 tangent theta cubed over 27 secant to the third theta times, I'm going to make this smaller. I'm not changing what I wrote. I just got to write it smaller. D theta. Okay. So I've got, this is 27 over 8. So I've got a 27 on top and a 27 on the bottom, right? So those can cancel each other out. So I've got 3/16 left for my fraction. I got a secant squared on the top and a secant to the third on the bottom. So I have a tangent to the third up top left. So, and then a secant left on the bottom. No, because I took the that 2 and that 3. So there's 1 left on the bottom. All right, so now let's change our secants and tans into sines and cosines. So we have 3/16 we can pull out in front, so I don't have to worry about that part. Tangent of the third is, it's going to be sine of the third over cosine of the third. And then secant is cosine, so there's going to be a cosine up top. So I'm going to be left with 2 cosines and 3 sines. Huh? No, that's cotangent. Sine over cosine. Yeah, one of the other, I think the last problem, or one of the first problems we had was cotangent, so that's why we had the sine, the cosine. All right, we're almost there. So we're here. Okay, now we've got sines and cosines. The nice thing about sines and cosines is I can do U substitution. Okay, so let's make U cosine. So then du is going to be negative sine. And then my U of 0 is cosine of 0, which is 1. And U of pi over 3 is cosine of pi over 3, which is 1/2, which is the very first problem I did class today. And then don't forget, we also have the sine squared theta is 1 minus cosine squared theta. So this becomes 1 to 1/2. The negative sign out in front. We have 1 minus u squared over u squared du. Now you know why I did that very first problem today in class. All right. So what can we do to make this a little simpler to integrate? Yeah, we can change the signs. We can switch this over. So this is going to go from 1/2 to 1. We also can clean this up. So this is the same thing as saying u to the negative second minus 1. Because we can divide both of those. So my integral is negative 1 over u minus u. And we're doing it from 1/2 to 1. Oh, actually, hold on a second. I screwed that. I messed up my sign.
Yeah.
No, I didn't. Did I?
1 minus u.
I don't like a
Negative u to the
random.
sorry. 1 minus u to the negative second.
Oh, because I messed that part up.
Yep.
Gotcha. Oh, no, I didn't actually.
No, you come down to the bottom there.
No, that's fine. Yeah. Because it's 1 minus or 1 divided by u squared is you. I flipped it. The book didn't. That's what I looked at the same thing. I went to look. I'm like, wait a second, and then I realized they didn't flip the signs where we did. All right, since I'm running out of space, and I did. Huh? I did drop the negative.
Wait, where did the negative sign come in the first place?
Negative sign. Oh, wait, yeah, negative sign.
I don't know how I can. I'm very confused now because I have like a eighth that I pulled out of the equation a long time. It's just been sitting outside the.
So we have, okay, so you did have an eighth, kind of.
Yeah.
You had the 1/8 there, right here. But you also had the 3/2. That's where the 3/16 came from.
Oh,
All right. So I'm not going to go through and do all this, the actual calculation stuff, because it's not that difficult. And don't forget, this whole thing was multiplied, which I didn't bring over, was 3/16. So the final answer was 3 over, I think it's 3 over 32. 3 over 32. That's the final answer. So the reason why switching the symbols out, that means I didn't have to go back, change back to theta, do the right triangle, change back to the original problem with the x's, and then plug in this actual steps. So it saved me like 2 more, or at least 3 more places that I could have totally screwed up signs and symbols and numbers and everything else. So let's look back at it afterwards. Here's 2 things that you really not necessarily need to practice before Thursday, but you definitely need to practice before the test next week. You really do need to go through and start working on some of these problems out and practice and look at the things. If you want the solution guides, remember, just send me an email. I will send you the solution guides completely done out, step by step. Okay.
So 3/16.
Yeah, I just didn't write. I forgot to write it on the slide.
Okay. That's
So, and no, I'm not writing them all out. The book gave them to me. So don't think you're putting me out by doing this. I have them. It's like literally a PDF. I'm just going to send it to you. It definitely will help you see where the little things that you could be mixing up are going to be. All right, go through, do the problem out, see where you're mixed up. If you get stuck, look at the solution guide, say, oh, that's what the next step is. Because that's going to help you start to recognize patterns that are formed. And I think that's the biggest thing with this stuff, is it's patterns. Once you start seeing the same thing over and over again, you can start doing them quicker. And I think that's where you're looking at right now, and I can tell on your faces, you're like confused. Because, and it's okay. It's totally okay. It's because you haven't done enough of them to notice the patterns on, okay, what's the next thing I should try? Like, even looking, the simple little things like going from tangents to the sines and cosines. Like, why? Well, because sine, cosine, or tangents and secants don't really have a nice, easy thing to switch back and forth. Sine and cosine does. So going to sines and cosines helps me there. It helps make the integration easier to do, even though it's the extra step there. Where trying to deal with it with tangents and secants, you could, it's just more complicated. Okay, so it's those little things. It's working with not screwing this step up here and doing the integral instead of the derivative, which is really easy to do. That's why I said it's not the integral of tangent, it's the derivative of tangent, because the integral of tangent is like ln of something, which would make the problem look even more complicated. So they're not going to, the whole point of trying to change this is to make it simpler. And that's why they're using the sines, the cosines, and the tangents, because that makes it simpler to switch over, or the sines, tangents, and the secants, because it goes over quite simply. But you got to start doing some of the problems to see those patterns. All right. So even though I don't assign homework, you do need to do it. Because if you wait until next week to try to do all this stuff and make sense of it all, you're going to bomb the first test. Okay. 2 things for tests, because my other class asked this, and well, I told my other class, and then I'll tell you guys now. So 2 things. First off, I will replace the lowest test grade that you get with your final exam. Okay? So whatever the lowest test grade you get, say this test you totally bombed, but you do well before the final, and you get, say you get a 50 on this test and a 75 on the final. I'll take the 50, it'll disappear, and I'll change it to 75. You don't need to tell me to do that. I automatically do it. Okay? So whatever your lowest test grade is, I will change and replace with the final exam. Second part of that is, if you were pulling an A in the class before the final, you're exempt from the final. So if you do well on all 4 tests, you don't have to take the final exam. Because there's no point, then I just replace your final exam with those scores. The opposite of the action. Okay? So, depending on which direction you want to go, if you don't do well on the first test or one of the tests, the final will take care of that. If you do well on all the tests, you don't have to take the final exam. All right? Yes.
I just want to write the final number.
Yeah. There you go. All right. Other than that, have a wonderful night, and I will see you guys on Thursday. When, if you thought this hurts your brain, Thursday definitely will. Huh? Yeah. It's Tuesday today. Don't worry. So the only days that I actually even have to recognize is Tuesdays and Thursdays. Like on Saturday, I'm like, is it Sunday, Saturday, Friday? Because other days I don't have to go anywhere, so it's like I totally lose track of time.
That's my problem.
The test is next Thursday.